So this lesson, guys, is a continuation of our quadratic pattern lesson that we did last week when we looked at the shapes and the different representation, the table, the words, the equation, and the graph. We're just looking at tables here, but if we were in class, I would ask you, what do you notice and what do you wonder? We're not in class, so I'm going to tell you what I notice. I noticed that in this first table here, my stage numbers are increasing by 1 each time. 1, 2, 3, 4, 5. And I noticed that my y values are increasing by 4 each time. From 5 to 9 is 4, from 9 to 13 is 4, 13 to 17, 17 to 21. Well, this looks very similar to something we did last semester, and we call this a linear pattern because it has a common difference each time. That term sounds familiar. When we did arithmetic sequences, we talked about a common difference. Now look at this other table here. This one looks very similar to some of the ones we were doing last week. We see that the stage number increases by 1 each time, just like it does in the other table. But when we find the difference between each of the y values, the difference between 1 and 4 is 3. Between 4 and 9 is 5. 9 and 16 is 7. So it's not common. It's not the same each time. But look what happens when we find the second difference. What that means is we find the difference of the first differences, if that makes sense. So in other words, from 3 to 5 is 2, from 5 to 7 is 2, and from 7 to 9 is 2. So that second difference is the same. And we know that if that's the case, that it's a quadratic sequence. And that common second difference is always going to be the case when you're dealing with a quadratic sequence. So we're going to look in detail at a couple of quadratic sequences, and just like last week, we're going to be trying to figure out an expression, an explicit expression that can be used to find the nth stage. All that means, guys, is we're going to write an equation that describes the pattern, okay? So we have stage number 1, 2, 3, 4, 5, and then the number of tiles, 6, 9, 14, 21. If we were to take the second difference here between 6 and 9, between 9 and 14, 14 and 21, we would find that the second differences are common or the same. But what we're going to do is try to figure out a relationship between the number of tiles and the stage number. Now, we did this the other day using patterns. Today we're just using the table, but we can still do it. We can still do it. Now remember, we're talking about quadratic patterns, and we know that in a quadratic equation we always have an x squared or an n squared, whatever our variable is. We're always looking for that squared term, just like we were looking for the physical squares in those patterns last week. So let's see what happens when I square my stage number each time. I have 1 squared, of course, which is 1. I have 2 squared, which is 4. 3 squared, which is 9. 4 squared, which is 16. And then 5 squared, which is 25. So what I have to figure out is, how do I get from this squared term to the y term? How do I get from 1 to 6? How do I get from 4 to 9? How do I get from 9 to 14? You see what I'm saying, what I'm getting at? And the answer is, I'm thinking, if I add each time, in this case, if I add 5, that's going to work, right? 5 plus 1 is 6. If I add 5 here, 5 plus 4 is 9. All right, same thing here. So each time, if I add 5, I get to my y term, my number of tiles. So how could we write that just for x in general? We know we're going to have x squared, because we've squared the term each time, x squared, and then I've added 5. So I can either say that y equals x squared plus 5, or if we're going to use function notation, I could say that f of x equals x squared plus 5. Now, it asks up here for the nth stage, So we could change that to an n. We could say f of n equals n squared plus 5. It doesn't really matter, guys. Whatever the variable is, we just need to be consistent in using it. All right, we tackled that one. Let's try another one, the second example. We're just given a sequence, 2, 6, 12, 20, and 30. And you may be just given a sequence on a worksheet or on an exam, so you need to know what to do with that. So I can create a table down here, and looking up at the sequence, I see that my first term is 2, my second term is 6, my third term is 12. Guys, I'm literally just copying down the sequence here. Fourth term is 20, my fifth term is 30. All right, so again, we know we're looking for a quadratic pattern, so let's see what happens when we square our term number. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And how do I get then from the squared term to my term value? How do I get there? That's the question. I have 1. How do I get from 1 to 2? Well, I could add 1. Right? But here I have 2 squared is 4. How do I get from 4 to 6? Here I would have to add 2. Then I have 3 squared, which is 9. I would have to add 3. 4 squared, I have to add 4. I'd have to add 5. Do you see a pattern forming here? Each time I'm adding the term number. You see that? So how could we write that for n? Well, I know I have to square the n, and then each time I'm adding the term number to the n squared. So my function could be n squared plus n. And you can write it like this: f of n equals n squared plus n. Of course, you could also use an x. But then it asks us, what is the 10th term of the sequence? Well, now we wrote our explicit function. Now it's easy to get the 10th term, right? We could follow the pattern. We've got the term down to the 5th term. We could keep going 6, 7, 8, 9, 10. But it would be a lot quicker if we just put the 10 into the function. F of 10 equals 10 squared plus 10, which is 110. So see how figuring out the explicit function helps us to find any term number that we need. All right, I'm going to go a little bit more quickly through this one because now you guys are getting the hang of it, I think. So we have our term values 2, 8, 18, 32, and 50. And we know that we want to square our term number in each one of these because we're looking for a quadratic pattern. If we found the second difference up here, we would find that the second difference is the same. So we have 3 squared, 4 squared, and 5 squared. Okay, now how do I get from 1 squared to 2? You could say I add 1, but let's think about this for a minute. There's another way that I can get from 1 to 2. I can also multiply by 2, right? Same here. I have 2 squared, which is 4. How do I get from 4 to 8? Well, I also can multiply by 2. Let's see if that continues to work. 3 times 3 is 9. If I multiplied 9 times 2, I would get 18. 16 times 2 is 32. 25 times 2. So you see a pattern forming. So really what we're doing with each term is we're squaring it, but then we're also multiplying it by 2. So we could write our function like this: f of n equals 2n squared. Okay, and then it's easy to find the 10th term. We can say f of 10 equals 2 times 10 squared, or 200. This example is actually exactly like the one we just did. We have the same values, 2, 8, 18, and 32 for our first, second, third, and fourth stage or term, like we called them in the last example. So I'm not going to actually go through it, but I did want to show you sometimes it will be represented like this. You'll have a table, look, it's the opposite direction. Has X and Y instead of term and term value. But it's the same thing, guys. Don't be thrown off when they show you the table like this. Our function would still be just like we got last time. F of n equals 2n squared. And when you're doing this on a test or on a worksheet, if it helps you to create your own table, just like this one, and put the terms in that way, you can. But don't be thrown off when the table is turned sideways and is labeled a little bit differently. All right, here's an example where we're given points. And that's a common way to represent a sequence, just by giving the points. But don't let that throw you off. We can make a table that helps us to organize our thoughts, and it does help me to organize my thoughts. So all I did was transfer these points down here to the table. So I have 1, 2, 211, 326, and 447, just like up here. All right, so let's see if we can figure out what this relationship is. So again, we're working with quadratic patterns, so we know that we are going to start out by squaring the x term, the input term. We know that that's going to happen because otherwise it would not be a quadratic pattern. All right, so let's see. 1 squared, that's actually just 1, right? 2 squared is 4, 3 squared is 9, 4 squared is 16. So I got to get from 1 to 2, from 4 to 11, that's not too tough, but 9 to 26, 16 to 47, these numbers are getting big. So I'm going to try something. Remember that last example, or one of the examples we did, where we had to multiply our squared term by 2 to get where we wanted. I could do that here. That still might not get me quite where I wanted to go, so I'm actually going to try 3. What if I multiplied my squared term by 3? In other words, 1 squared times 3. 2 squared times 3 each time. Let's see what happens when I do that. All right, up here I get 3, excuse me. If you guys were watching me teach, you would have corrected me, I'm sure. 1 squared times 3 is 3. 2 squared times 3, that's 4 times 3 is 12. 3 squared is 9, times 3 is 27. And then 4 squared is 16, times 3 is 48. Now look at this. This looks promising because look, I have to get from 3 to 2, from 12 to 11, from 27 to 26, and from 48 to 47. Each time I'm subtracting 1. So I'm thinking that it would probably work to say that our function could be f of x equals 3x squared minus 1. All right, here we have our last example that I'm going to show, and then you can try them on your own. Again, we have the table that's sideways, but don't let that throw you off. If it helps, draw the table the other way. Go ahead and draw it the other way. So you have 2. Notice there is no first term here. They didn't show us what the first term was. We only have the second term, third, fourth, and fifth terms. So they are 18, 28, 42, and 60. So we're going to have to figure out what this relationship is, just like we've been doing. So we're going to start out with, let me change colors here so you can see it a little bit better. So I'm going to start out with squaring my x term, 3 squared, 4 squared, and 5 squared. All right, which is, we're dealing with 4, 9, 16, and 25. All right, now we have to figure out how can I get from 4 to 18, from 9 to 28, from 16 to 42, and from 25 to 60. We're dealing with some big numbers again, so let's think about that for a minute and see if we can figure out a pattern. We could try some different things. We've tried multiplying by 2, multiplying by 3. Let's just see what would happen. What if we multiplied each time by 2? Let's see what happens. 2 squared times 2, 3 squared times 2, 4 squared times 2, and 5 squared times 2. What do we get? We have 4 times 2 is 8, 9 times 2 is 18, 16 times 2 is 32, and then 25 times 2 is 50. So I'm seeing kind of a pattern here because now I have to get from 8 to 18. I have to get from 18 to 28, from 32 to 42, and from 50 to 60. Each time it looks like I'm adding 10. So what if we tried this? What if we made our function f of x equals 2 times x squared, because that's what we did here each time, 2 times x squared, and then I added 10. So the question is then, if we did that, what would be our first term? We could figure out what our first term would be. If we put 1 in for x, f of 1 equals 2 times 1 squared plus 10, or 12. So we would know our first term would be 12. So guys, I know it's a little bit tricky sometimes to figure out these patterns, but just try things. Try adding the same number each time. Try, in one of the examples, we added back the term number each time. Sometimes we need to multiply by 2 or multiply by 3, but in the following examples, you'll be able to give those patterns a try yourself. And remember, Ms. Holt is checking her Go Formative. So if you need help or you have a question, just send me a message and I will answer you as soon as I can.